Here we consider another example involving spring potential energy. Let's shift over to the problem itself. Find the final speed of the object. Often a good sort of thing to ask in a conservation of energy type problem. Assume the surface is frictionless and also that m, the mass, is 0.5 kilograms and k, the spring constant, is 12 newtons per meter. In the picture, additional information is provided. We have the mass at time 1. A little different notation here. Instead of initial and final, we'll have time 1 and time 2. When the mass is at time 1, its position is 0.2 meters and its speed 3 meters per second. At time 2, the mass is at negative 0.1 meters and the speed, that's what we're trying to find out. The spring isn't drawn in this picture. Just to simplify it, it's stretching from the wall over to the mass, whether it's at position 1 or whether it's at position 2. So how are we going to set up and solve this problem? Here's a small picture so we can still take a look at that. And, well, conservation of mechanical energy, I think, is going to get the job done once again. It's kind of a recurring theme in these problems. Mechanical energy at time 1 will equal mechanical energy at time 2. Here with the mass moving on the horizontal and connected to the spring, there will be the kinetic energy and also the spring potential energy. So we can replace mechanical energy with the sum of kinetic and spring potential at time 1 and again at time 2. The kinetic energy, 1/2 mv squared, and the spring potential energy, 1/2 kx squared. The values at time 1, the values at time 2. Notice this time, in contrast to the gravitational potential energy problems, the mass does not appear in every term. The mass is not going to cancel out. It needs to be included in this problem. Substituting in some values, the mass is 0.5 kilograms. The speed at time 1, 3 meters per second. The k is 12. The x1, the position at time 1, 0.2. The final speed, that's what we don't know. Let's just call it v. The spring constant, the k, still is 12. And the position at time 2 is negative 0.1 meters. And that's squared. And this can be solved to get that the speed at time 2 is about 3.12 meters per second. So again, another application of the conservation of mechanical energy. It's sort of all in the algebra, but these are good problems to work through.